So this week we have 4 lectures, right? So you are happy? You are very happy. Okay. Okay. So last time we started to see the first simpler. The simplest, let's say, but not really the simplest, because the simplest is the inertial oscillation. But one of the simplest solution for the Navier-Stokes equation in rotating framework, which was the geostrophic flow. Okay, and we found that geostrophic flows are isobaric. They are non-divergent on the F-plane, and also we found that the solution is quite easy, quite simple, and practically we see that in the northern hemisphere, flow rotates, leaving on the right the high pressure and on the left the low pressure. Okay, so this is the example that we saw last time. We can also apply them to ocean dynamics, and for example, if we consider the gyre, the major gyre that circulate in the Atlantic, in the Northern Atlantic, we can have something which is similar. So we can easily describe large-scale flow which satisfy to the hypothesis of geostrophic flow in a very simple manner. So we can do something more and try to consider an irregular bottom. So what happened if we have, so far we never talk about bottom, we consider the bottom as flat. Now we want to consider the bottom with some irregularity. So the layout that we can consider is two-dimensional, so we can have here the direction x, the vertical direction here. We can consider that this can be, for example, the atmosphere, with this is the troposphere, so a sort of discontinuity surface, or this can be the ocean, and this is the discontinuity between the ocean and the atmosphere. So the entire height scale is capital H, and this is the depth, which is small h, and of course this is the vertical coordinate, which is capital H minus h. Okay? Which obviously, in the most general cases, we can consider that we have the epsilon going inside the blackboard. So, in the most general case, we can have a sort of topography, right? So let's think about a parcel which is here, okay? So our question is, will this parcel will able to go up or down? So if we are in the F-plane, we said that we have the non-divergent, so the flow is non-divergent. So the xu plus the yv is equal to 0. Okay? So we just started 1 minute ago, just considering the geostrophic flow with the irregular bottom. Okay? So just this is the bottom, so this is our solid bottom. And we were wondering what happened if we consider a parcel here. So if the parcel is going up or down. So if the parcel is going up or down, let's consider the upward direction, it will have a velocity which will have u over the x direction and w over the vertical direction. Okay? So w is nothing more than the time variation in z. Okay, so this is the usual definition for the velocity. So we can express this as the local direction plus dz dx plus v dz dy plus w dz dz. So I simply, it's quite strange, but in any case, z is a function, in general, could be a function of x, y, and t. In our case, we have that z is a function of x and y, because it's capital H minus hxy. Because for our case, there is no change in time, okay? So the bottom topography, of course, remain the same in time. So we do not have any kind of change in the surface. So according to this, we can delete this. We can also delete this, because if we substitute z to this, we will have u. So z is h minus capital H minus h, which is a function of x and y. So this will be minus h dx. Then we will be minus v dh dy. And this is 0. Okay? But what we remember from the geostrophic flow, if we are in the F-plane, which is quite easy for us in this moment, we have that the geostrophic flow, we said, are natural non-divergent on the F-plane. So it means that there is no variation in the vertical dimension. Okay, so vertical velocity is constant. But we said, be careful, since we have solid boundary, and we cannot have any kind of generation of mass, we have to take W is equal to 0. So it means that this W has to be 0. So if this W is 0, it means that we have a conservation, let's say, of the U multiplied by the gradient of H. And the gradient of H is nothing more than the topography. So how the topography is changing in the XY plane. So what does it mean? What does it mean this? So you said last time that for the geostrophic flow we saw this one, no? Yeah. We have something similar here. Yeah. So not just geostrophic flow are isobaric, but they also follow the isopath. So it means that they must be perpendicular to the line of equal depth. So this flow will never go nor here, but only here or here. Okay? Because so geostrophic flows are isobaric and isobars are isobaths. Why? Because we are having the hydrostatic approximation, which always keep the rule. So, in this case, for example, we have that the gradient of z is positive. Okay? Because we are going, z is increasing along x. So if this is positive, it means that the xh is negative, but it's because there is a minus. So when I have this one, it means that since in this case, for example, I don't have any change in y, in this specific case, okay, think about a symmetric case like this. So the only possibility is that this case is positive. So this is positive, and so we can have only a vertical V, which is negative. Okay? So U, the xh plus V, the yh is equal to 0. So U, V must be perpendicular to the xh, the yh. Okay? So we will have that the V velocity will go inside the black body. So this can be very nice seen, like in these cases, because if you take the geostrophic solution are minus Fv equal to minus 1 rho 0 the xp and Fu equal minus rho 0 the yp. So since P is rho 0 GH, okay, we can substitute this here and we have that minus G the XH minus G the YH. So V is exactly proportional to dxh, okay, which is this dxz. Okay? So in this case, we can calculate for the Mediterranean Sea, for example, starting from the absolute topography, which is practically this one. Okay. So the absolute dynamic topography is the distance that we see from the top of the surface of the ocean up to the satellite. Okay? And even if it's something like centimeters, because these are centimeters, so it means that you have a topography which is positive here, where it is red, and negative here. So if we look, for example, in this position here, we have that the h over the y, it means that we are going from this direction to this direction, okay, along the y direction. So it is decreasing, right? Because we are going from high value to low value of h. So if it is decreasing, it means that this number here is negative. So negative minus, it means that this is all positive. So u is positive indeed. The geostrophic velocity here is in that direction. Okay? So in a closed basin like Mediterranean Sea, you have that the velocity is geostrophically adjusted, and it follows this direction in first approximation, leaving the coast on its right. Okay? Exactly like in the geostrophic flow that we saw last time, the flow leaves the high pressure on its right. Okay. So it's another interesting thing is that since the geostrophic flow must follow the isobath, they occur only on closed isobath. So if we have something like this, and this is like a topography, okay? So this is exactly like this thing here can be a section of this one, okay? So we are going, for example, 10, 20, 30, whatever, okay? So we are going up, or if you like, down. So this is a mountain or a hole. So since our geostrophic flow must follow the isobar, so it means that it can go only in this direction, but can never cross the isobar. Okay? So geostrophic flow never cross isobars, never cross isobar. And this is a phenomenon which is also called Taylor columns. So if we have any obstacle, the geostrophic flow will be able to circumnavigate the obstacle and never cross the obstacle. Okay? So if we have like a bump or a hole, we will have only something like this and like this, or like this and like this. Never. This is not allowed. Okay? Because of the vertical rigidity of the Taylor-Klugman theorem. Okay? So we cannot change the velocity, the horizontal velocity in the vertical. Never for geostrophic flows. Good. Okay, so now we may be quite satisfied for the geostrophic flows, but we can move a little bit further and try to relax the strong hypothesis that we made for, for the geostrophic flow. So, for the geostrophic flow, we said homogeneous fluid, and we are okay. Then we said Ekman was much smaller than 1. Okay, so we are far from the boundary, so we do not consider boundary layer. Then we said these two much smaller than 1. Okay, in this case, we allow them to be smaller or slightly ordered than 1. So it means that in our primitive equations, if for the geostrophic flow we neglected this one because of Ekman and this one because of Rossby temporal much smaller than 1 and all this because of Rossby much smaller than 1, now we still neglect the friction, so we still are far from boundary, so we still keep Ekman much smaller than 1, but we allow the 4 terms here to remain, still keeping the no shear condition. Okay? So we will have du dt plus u du dx plus v du dy. We don't have du dz because of this one. Minus fv equal minus 1 rho 0 dp dx. Then dv dt plus u dv dx plus v dv dy plus fu dx. Then we have simply 0 dp dz, and then we have the continuity equation. Okay? So we made a good advancement with respect to geostrophic, because geostrophy is all without this one. Okay, so geostrophy is this one. If we solve u and v, we will have the geostrophy. But if we allow to have Rossby numbers order than 1, we may take also the local derivative and the advection, the horizontal advection. So from the geostrophy, we found that this the equation, the continuity equation, just reduced to a horizontal divergence equal to 0. No? Yeah.
The second line.
The second line, this one.
Yeah, why is it dp dx?
Sorry. Thank you. It's not a question, it's a correction for me. It's an observation, yes. Okay, so now we want to say what happened in this kind of flows, which we call barotropic. So these are so we are moving from the geostrophy to the barotropic flows, which are basically defined by the no shear. Okay, so when you listen about barotropicity, barotropic instability, the barotropic is the attribute barotropic always deals with the fact that you don't have any change in the vertical. Okay, in the atmosphere and also in the ocean dynamics, you will also listen baroclinic, which is nothing with medicine or baroclinicity means that this is no longer 0. Okay, so and you have two different mechanisms, two different instability. Baroclinic instability, barotropic instability, which are very different in the world. So this is much stronger in the tropics, of course, this is much stronger in the mid-latitude. But now let's remain in our very ideal case. So for the geostrophic flow, we said that this was reduced to simple horizontal divergence equal to 0, and W was 0. So in this case, we don't have any kind of, let's say, hypothesis to say that we also have the vertical velocity 0. So we don't know. We don't know. We have to calculate. So one thing that we can do is, again, to consider a system where similar to the previous one, but dynamic. So we will have x, z. This surface is the bottom surface, and this is the water depth or atmosphere depth, whatever. So again, this can be the land, and this is the atmosphere, and this is the discontinuity at the end of the troposphere, or this can be the sea bottom, and this is the ocean. Okay? So, quite obviously, the bottom does not change. Yes?
For baroclinic, you said that one never be 0. Means
for the baroclinic, you can have shear.
It means there is always a change in the vertical.
There is, sorry?
There is always a change in the vertical.
Yeah. Yeah. Also because we are dealing with homogeneous flows, okay, which is much easier. With baroclinicity, you always have to take something which is not homogeneous. So you have stratification, and when you have stratification, things become much more complex. Okay, we will see something at the end of the lecture. Okay, so this is the bottom, this is bottom, or the topography, and this is the let's say the height of a fluid column. Okay, can be water column or air column, and this is moving. Okay, so it's changing in time because we have some velocity flows here, which is transporting this column. So one thing that we can do is to calculate, to integrate the equation of continuity. So we can integrate between B and B plus H. So from here to here the equation of continuity, dxu plus dyv plus dzv in dz, which of course will still be equal to 0. No? So it's just a sort of integral form of our continuity equation. So we can separate the two terms. One is horizontal and one is vertical. So we will have these two terms here. We know that they are independent by z, so we can safely put them outside. So we will have dxu plus dyv b plus h dz plus b plus h dz dz equal to 0. Okay, so this, how much is this? H. Okay, so we have the xu plus the yv multiplied by h. And this?
WH.
So this will be w computed in b plus h minus w computed in b. Good. Okay, so now we have to calculate these two, similarly to what we did before. So we can. Okay. So w in b plus h will be dz dt in b plus h, which will be d z dt local b plus h plus u dz dx b plus h plus v dz dy b plus h, and that's all, because since z is equal to b x y plus h x y t, we don't have any kind of dependency on z. So the third term is 0. So now we can say that dz over dt is just dh over dt, right? Plus u dz dx over, sorry, dz over dx for b plus h will be db dx plus dh dx. And this one, similarly, db dy plus dh dy. We can do the same at b. Easier because b is constant in time, so we just remain with u db dx plus v db dy. Okay? Which is nothing more than the one we found before. Okay, in the previous case. Okay, when we subtract this from this, the only term that will remain are this one, and this one. So all the terms with b are disappear. So we can say plus dth plus u dxh plus v dyh equal to 0. So these three terms here are the local derivative of h and the advection of h due to the horizontal current. So I can write these three as a total derivative of h in time. So it means that our continuity equation transforms in something which is 1 over h dh dt equal to minus we can say this. So with this h here, I consider only the horizontal divergence, which is this one. Okay, so this one is this one. Okay, so my continuity equation, that one, has been transformed into an equation which tells me that the variation of h, which is the height of the column, of the fluid column, air column or water column, change in respect to the horizontal and vertical horizontal divergence or convergence. So if we have divergence, this term is positive, okay, with divergence. With the minus is negative, so we have that this is negative. Okay? So divergence means that this is going to decrease. If I have convergence, this is negative, positive, and then this is positive. So convergence and the column increase. So this is another way to see the mass conservation. And we can also make a step further. So we have another, we can write it here. So we can write this or this. You know that you can play with the derivative. So we can also write it dh dt plus, we can put together this term and this term and just have the dx hu plus the y hv, which is another way to say that the flux of mass, because if you consider h and you take the surface, the cross section of this column, like ds, okay, like an infinitesimal water column, this is nothing more, and you multiply everything by ds, which is a constant, you can have that this is exactly the conservation of volume. Okay, so we can still say something like this, and we will arrive to this. So we will arrive to this one later. Okay. So the important thing now is that now we have found a new set of equations which we call shallow water model, and which practically is equal to the sum of the local derivative of u and t, the two advection horizontal, the two Coriolis term, and the pressure gradient, which has been here written according to the hydrostatic approximation. Okay, so just changing P in G rho multiplied by H. And then we have the new continuity. Okay? This is very important because we moved from a system of 5 equations. Can I decrease a little bit? Because it's 26. I was ready. So we move from 1, 2, 3, 4, 5 equations into 3. Of course, we are in homogeneous conditions, so the equation of energy naturally is removed. But still, we were able to put together the third equation of momentum and the continuity in one single equation, which is this one. So this shallow water model is quite useful, and this is the case when B is equal to 0, so when the bottom is flat. Okay, so there is no topography, but the bottom is flat. Otherwise, you should change here and put H plus B. Okay, and it's very useful to study some specific cases in ocean and in atmosphere. And it's called shallow water because it's based on the fact that this, let's say, this situation here is considered historically for very low water depth. Okay? So it was conceived at the beginning for a shallow water environment, but can be applied both to the ocean and to the atmosphere. So, if we now take into account the first two equations, we can make some more assumption because we have never considered nothing concerning vorticity. So I can make the vorticity. You remember you can calculate vorticity by making the vectorial product between the differential operator and the velocity. So since we are dealing with flows which have a very specific horizontal characteristic, so it's something that, as we have seen, is strongly characterized by a horizontal, by the horizontal properties. So we can consider only the vertical component of vorticity. So if we calculate K, this will be the XV minus the YU. Okay? So this is the vorticity, we will call it zeta. Relative vorticity. So if I am in the horizontal plane, xy, and I having a flow going like this, of course, every point of this plane will have a vorticity, which will be in this direction or in the other direction. Okay? So I will never, since the z over du, the z over dv are always 0, the only possibility that I can have is this one. Okay? So I'm interested to study this, the evolution of the vorticity. So to calculate the evolution of the vorticity, I have to take, so if I have three equations, 1, 2, and 3 over there. No? So I will have to take the y derivative of the first multiplied by minus and x derivative of the second. And then I will take the sum. Okay, if you like, I can do every single step, or I can leave it by homework, as homework. It's not difficult. What do you prefer?
This one goes there.
Okay. Okay, so, but you have to help me, okay?
Okay.
Because I will be lost. Okay, so, first, dy over dtu, then plus dyu dxu plus u dxyu. It's okay?
Why is the minus? Sorry.
Okay, let me do like this.
Oh.
Okay? So we don't lose minus terms. Okay. Then dyv dyu plus v dxyu minus dyf v minus f dyv equal to minus g dx yh.
Sorry. I'm sorry.
You are ready?
What are we do? Are we taking the minus dy of equation?
Minus the y of the first and the x derivative of the second. Because the first equation concerns u, the second equation concerns v, and we are interested to zeta, which is the x v minus the y u. Okay? So we want to calculate the evolution of the vorticity. So since we have here the evolution of the velocity, the two components of velocity, we just compute their partial derivative in x and y, and in order to have all the terms. So the y dt du, the y du, the x du, u the xy u, the y v, the y u, v the y xu, the yf. Okay. Now x. So we have the x, the tv plus the xu, the xv plus u, the x square v I told you you had to help me. Okay. So x the x view plus, so the x v the y v plus v the x y v plus the x f u plus f the xu minus g the xyh. Okay, when we do the sum of this, of course, since we are now we can take the minus. So minus, 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 plus, plus, plus. This is 0. And now we can start to take first time derivative. So we have the first two terms, which are the xv minus the yu Okay?
Are we adding?
Sorry?
Adding the
Yes, I'm adding like this. So I'm going to do this, okay? And then I will also allow, which is not written here, to add f, okay? Of course, the TF is equal to 0, so I can add it, no problem. So I can leave that one. Then I have plus u dx advection. So u dx, I have dxv and this one. So it's minus dyu. Then plus v dy. So v dy. So it's the minus, okay, dxv, and this one minus dyu. Then I have u dxy, this one. Sorry, thanks for that. I told you, you are not helping me.
We are trying.
So, u dx v, u dxy u, this one, then v dy, this one, and v, this one. Okay. Now we have dxu and dxu, dxv minus dyv plus dyv, dxv this one, minus, which was this one, the yu. Okay?
Sir, dyu in that.
dxu and dyv.
Minus dyu, I think. No.
Minus dy, yes. And finally we have plus. So we have the y v multiplied by the yf. So the yf, so is v the yf. So I can put it here. Okay, v the yf. And
You
no,
also
this one, not this one. And then this one.
in the second expression. Here.
Yes. And then I have f dxu, yes, plus the yv. Okay, so I can put together this one, and I just have the xu plus the yv, and again this one. So this will be plus f, and this is like this. Okay? So in any case, you have to do it as a homework, okay? Because I can ask this to the exam. Okay, so what we have? We have an expression which is dxv minus dyv du plus f, the same, which is here with the local derivative in time, here with the advection, and here multiplied by the horizontal divergence or convergence. So what we have, which is equal to 0. So what we have is d dt of, this was theta. So this term here takes the local variation and the to advection, which is equal to the horizontal convergence or divergence multiplied by this term here. So this term here is equal to the relative vorticity plus F, which is the ambient vorticity, is the Coriolis term, by the way. So it's the local vorticity of the system. And this is very important equations, which says that the total vorticity of our flow is minus here, is regulated by the horizontal divergence or convergence. So the variation in time, we can write it here, 1 over theta plus f d dt theta plus f is equal to the horizontal divergence.
The total vorticity is related by what?
The total vorticity is related to the horizontal divergence. So exactly how this equation here told us that the variation in time of the height of the fluid column is equal to the convergence, the horizontal divergence, we are having a similar equations for the total vorticity. So now, if we consider this fluid parcel, okay, fluid column, which is rotating, so it will have a vorticity, which is the sum of the ambient vorticity and the relative vorticity, a height. So when we have a divergence, it will go to decrease to increase the surface and to decrease the vorticity and decrease also the height. So this is going to is intuitive, but we have to find it the equation. So if we just consider the fluid parcel with ds, we can say that the variation in time of ds is equal to dxu plus dyv ds. Okay, so how the surface is enlarged or decreased in time, it depends on the xu, the yv. This is this one. Okay, always the horizontal divergence convergence. So of course, if I'm having a fluid, since the fluid parcel is the control volume, no? You remember from the fluid dynamics course. So it's the control volume. So if I'm going to have a convergence, this is going to decrease, this is negative. If I'm having a divergence, this is positive, and this is going to increase. So from this, I can put together and, for example, multiply by h. So I will have h d dt ds equal to h ds. So and this one, which is 1 over h. Okay, here. I multiply this by ds. So I have ds over h dh dt, which is equal to minus so, okay, this is even not, so I can like delete this one. If I do the sum of these two, I will have, yes, where's the problem? Ah, no, yes, this is ds, and ds over h. dt h ds, which is equal to 0. Okay? Because this one is h dds dt plus ds dh dt. Okay? So dds dt is this one, dh dt is this one. Okay? So if you put all together, you will have, which is that is equal to 0. One more thing is to make to calculate this one and to multiply by ds. So if we multiply this by ds, what we will obtain is that form here. Because the trick is always remove the presence of the divergence. So when we obtain this, which is the conservation of the angular momentum, we have exactly this expression here. So what happened is that if we have an increase in the vorticity, we will have a decrease in the surface. Moreover, if we have, we can also look at this in two terms. So if fds is increasing, we have to decrease zeta ds. So fds increasing means that the fluid column is traveling towards north. So if the fluid parcel is traveling towards north, it means that its relative vorticity has to decrease, and the contrary. So we may have another form of this equation, still playing.
Are you adding this two?
Sorry?
Are we adding this two? The two?
Yeah. We can also consider, since we have that f this is conserved, and also this is conserved. So this conservation is quite obvious. It's the conservation of the volume, okay? Since we are dealing with the incompressible flow. So also the ratio between these two terms will be conserved. So the ratio is actually d dt f plus zeta over h. So this new quantity here, f plus h, f plus zeta over h, is called Q and is known as potential vorticity. So
Sir, how we get that third expression?
this one, by taking the ratio between this and this. Okay? If this is conserved and this is, this is one of the way, you can just also play with all the other conservation equations, and you can just multiply one of the other or divide one of the other, and you will obtain this one. Okay? So if you like, you can just make the variation of the differentiation of these two, and you will obtain each of the other conservation. So continuity equation, conservation of mass, of volume, conservation of vorticity, that is conservation of vorticity with respect to divergence, horizontal divergence, and conservation of height with respect to divergence. Okay?
Where is the potential vorticity?
So the potential vorticity is defined by this term here. Okay? So is the ratio between the total vorticity and the h.
The ratio between the two.
Sorry?
The ratio.
F plus zeta ds divided by h ds.
Equal is that one, the last one.
And we obtain this one.
Okay, answer equal.
So they are like the ratio, if this is equal to 0 and this is equal to 0, also the ratio between them is equal to 0, the time derivative.
Sir, is that third term just the approximation? For example, d open dt something equals to 0. Means
Sorry,
something
can you repeat?
that, for example, in the first term, d open dt, that term is equals to 0 means that term is equals to something constant. Yeah? Yeah. And the second term is equals to something constant. But that constant may not be equal.
Yes, but even if the constant is not equal, the variation in time is 0. So it means that this is a constant in time. This is a constant in time.
Yeah.
Okay, so the fact that their ratio is still a constant, it means that they cannot change in time.
The Q is F plus J over H.
Q is F plus zeta divided by H. Okay, so this formula here is also known as Kelvin's Theorem, which says that in barotropic flow the circulation is conserved. Do you remember what is circulation? You should have done it in fluid dynamics.
Integral.
around the closed curve.
And is also known as vorticity flux. Okay? So the circulation is UdL over a certain closed path, but this is also can be written as the vorticity
Yeah, surface integral.
integrated on a surface. Okay? So this is exactly the same. Okay? So we are saying that we are conserving the circulation or the vorticity flux. So the vorticity flux is, the flow can be squeezed or stretched, but the vorticity will remain the same. And in this case, the vorticity is not just only the relative vorticity, zeta, but the sum of the relative vorticity and the ambient vorticity. Okay? That is very important because without the ambient vorticity, so in normal fluid dynamics, you will have only zeta. In GFD, you have also the effect of F. So if we are over an F plane where F, of course, is constant, we will have only zeta over H. But if we have that, for example, the Coriolis term is much larger than the advection term, okay? So it means that these two, between these two, this will be much larger than this one. So the relative vorticity is much smaller than the ambient vorticity. So we will just have F over H. So having only F over H, it means that if you want to conserve F over H, it means that if a parcel moves to north, F is increasing, so H should be decreasing. And if a parcel moves toward south, F is decreasing and H is increasing. Okay? So the conservation of potential vorticity is at the basis of one of the most famous models which explain how the Atlantic circulation, the Atlantic gyre, is like we have seen in this picture. Okay? And explain you that if you have a certain wind which is blowing this direction, which is giving a certain configuration of the stress over the sea, over the ocean in this case, you will have that thanks to the potential vorticity conservation, you can have a model which exemplify in a very, very simple way, in a very clear way, the circulation of the Atlantic gyre. Okay? Of course, then you have to consider the Ekman dynamics, boundary layer, and so on, but the vorticity, the conservation of potential vorticity is at the basis.
So you said the conservation of potential vorticity is the same as Kelvin circulation theorem?
Kelvin circulation theorem is only the conservation of vorticity flux. Okay, so it's only that one.
Okay.
This is something more. Okay, so conservation of potential vorticity is a characteristic of barotropic flow that adds up to the Kelvin's theorem. Okay, so now we want to move to a new topic, and
Excuse me. It's not clear for me.
this.
Yeah.
Okay, so I can rewrite everything if you like.
The final explanation about.
So if this is constant and this is constant, also the ratio is constant.
Yeah.
But you can also keep these four equations and play with them in order to obtain this one and this one and then this one. Okay? So because all of them are related by the fact that you have the variation of volume, the variation of vorticity, the variation of height. You can also, for example, if you like, you can do that from here. Okay, so from here you multiply this by zeta by f, zeta plus f, and you have zeta plus f here. Okay, here you can leave it like this. Yes, you can just keep this one. If you like, we can do it. just to don't leave anything. So this term is equal to this term, and this term is equal to this term, right? So 1 over okay? So so if I have so this is 1 over h okay? This one is, so d dt 1 over h is minus 1 h squared dh dt. Okay? So since this is equal to 0, so we have, or, well, you can, don't say that, but we say that 1h over dt, so this is minus 1h squared so 1h, which is this one, so this is 1 plus h. Okay? I put minus 1 over h multiplied by this one, and I obtain 1 over h dh dt. So 1h dh dt is this one. So I can have 1 over equal to
minus exactly same.
minus, oh wait. Ah yes, sorry. Not this one, this one. So I have 1 over h minus.
This is 1.
Okay? Really, you can play. You can play because all these equations are true, of course. And so if you are careful with the sign and the and the multiplication, you can have all the equation rewritten and retransformed. Okay, so now it's time to move to starting to considering the boundary layer. So up to now we always consider Ekman number much smaller than 1. You remember? So Ekman number much smaller than 1, and Ekman number was the ratio between the frictional terms, second derivative, and the Coriolis term, which scales like ni u L squared h squared over omega u, which is equal to ni omega h squared. Okay? So let's try. Okay, we already said that Ekman is much smaller than 1, but we can take ni and consider. Okay, ni for, you remember last time we talked about molecular diffusion or molecular viscosity and eddy diffusivity or eddy viscosity. Okay, so molecular viscosity is 10 to the minus 6 for water square meter per second. The eddy diffusivity is 10 to the minus 2. Okay, you remember we talked about also thermal diffusivity, everything which is eddy, turbulent or eddy diffusivity, we can consider this as a value. So if we are at mid-latitude, omega is 10 to the minus 4 secant to the minus 1, and h can be, let's say, 1000 meter. Okay? So let's say how much we obtain with Ekman. So we have 10 to the minus 6, and then we have omega, which is 10 to the minus 4, and h squared, which is 10 to 6. So this is second. So this is 10 to the minus 2, so it's 10 to the minus 4. Okay? Which is, of course, much more than. Of course, if you take 10 to the minus 6 here, it was, yeah. So, 6, okay, no, it's the same. Okay, so this is valid far from the boundary. So if we have a boundary, we will call it this part interior, and then we have the part which is called the boundary layer. So according to Prandtl hypothesis, Prandtl said that when a flow is interacting with a boundary, with a solid boundary, we will have a part which we call interior, which doesn't feel the solid boundary, and a part which is called boundary layer, where all the properties are, the velocity properties are constrained by the presence of the bottom of the solid boundary. So if we have, for example, a geostrophic flow here in the interior, it will happen that with a certain low, this flow will have to go and reach u equal to 0. So the fact that the Ekman hypothesis of having Ekman number much smaller than 1 removed the second derivative from our equations, practically had to allow the possibility to have the slip condition here. Okay, but this is not true. So this is something that we consider for the geostrophy, to say, okay, we can allow to have slipping over close to the boundary. But of course, this is a strong, very, very strong approximation, because close to the boundary, we should have velocity equal to 0. So, Ekman number here is much smaller than 1. When we are close to the boundary, Ekman number start to be order than 1. So if this, let's say, is h, okay, the total height is capital H, the depth or the layer of the Ekman has a dimension d. So
D what? Sorry.
d is the scale for the boundary layer. So if we have Ekman, which is ni omega h squared, much smaller than 1 in the interior, in the boundary layer, we will have Ekman, which is ni omega d squared, which is order than 1. Okay? So, with d much smaller than h. So this section here I have strongly exaggerated the plot. So this section here is much smaller actually of the entire height of the flow. So let's try to evaluate it. So if Ekman is order than 1, it means that d will be order square ni over omega. So if again ni eddy is 10 to the minus 2 and omega is 10 to the minus 4, so this will be 10 to the minus 2, 10 to the minus 4, so we obtain 10 meters. And if you remember, we had before h 10 to the 3 meters, so 1 kilometer, okay? So d is actually much smaller than h. So over a basin, which can be the ocean, an ocean basin, or also on the atmosphere, the layer where the flow feels the presence of the solid boundary has a depth which is much smaller than the entire height where the flow is moving. Okay, so we can keep this here. And we can come back to our equations. So, starting again from the primitive equation, we can consider again rho equal to 0, rho b much smaller than 1, temporal rho b much smaller than 1, so we can neglect all this. And we just keep no longer Ekman much smaller than 1, but Ekman order than 1. And so we have Coriolis, we have the pressure, and finally we can keep the friction. So in this case, as you remember, we considered eddy viscosity and eddy diffusivity as a function of Z. The Ekman model actually taking consideration constant values of of the viscosity. So the equations are this one. So allow me to keep or not E. So you consider that this is eddy viscosity. Okay, so sometimes I will put, sometimes not. So please forgive me. Then we have 0. Okay, so now we have to consider boundary condition. So the boundary condition are that when Z is much smaller, let's say Z going to infinity, okay? So we are very far from the solid boundary. it happened that our flow here, U will be geostrophic and V will be geostrophic. So simply what happened, when we are very far from the solid boundary, again Ekman become much smaller because we are far from the boundary, we don't feel the boundary, so we can neglect safely these two. Okay? And we obtain, again, the solution of geostrophy. The very novelty is that when z is equal to 0, we have u and v equal to 0. So it's something that before we couldn't consider, because as you remember, for geostrophy we allowed the slip condition, which is not, let's say, not natural, but in that case it's like we didn't have any boundary layer. So the boundary layer doesn't exist and there is only just an interior. So now the boundary layers start to exist. And another interesting thing is that the value of the boundary layer is constant. So let's say constant. It depends on the viscosity and on the rotation. So if rotation goes to 0, what happens?
Infinity.
So the existence of this layer, which is called Ekman layer, and this is the Ekman depth, is just because, is just due to the fact that we are having a rotating fluid. In normal fluid dynamics, if you have a boundary layer, which is like, let's say, if you consider like a plate, you have a flow here, and you have a boundary layer which is developing like this. Okay? So if this is the x direction, this is the depth of the boundary layer, this depth actually is a function of x, because it increases with the x direction. In our case here, the boundary layer always exists. So for a rotating flow, we will always have a boundary layer, which is called Ekman layer. Actually, Ekman had, from his professor, who was Nansen. Nansen was a Norwegian professor who was also an explorer and went to take a lot of data in the Arctic Ocean. So he gave to Ekman, who was a young student, a thesis trying to explain why he was observing from the ship that if the wind was blowing this direction, the iceberg were drifting in this direction. Okay? So he was very puzzled. So why is possible if the wind is going this direction, the iceberg should be parallel to the wind? But it was not like that. So Ekman had to solve this problem mathematically using this model in order to explain how was why the iceberg were drifting on the right of the dominant wind. And this was then, this became then famous as the surface Ekman layer. Now we are starting to study the bottom Ekman layer. Okay, so we have a bottom here, we have an interior which is geostrophic, and we want to see what happened to the equation, to the velocity in the boundary layer. So we can also consider one more approximation is to consider P as constant. So P is just a function of x and y. And we can put our interior flow, geostrophic, parallel to x. So it means that the geostrophy is simply UG 0. Okay? So we align our frame of reference with the x component of the geostrophic flow. So if we solve this, as we said before, far from the boundary, we will have that V will be Vg, that will be minus 1 over rho 0 dxp, and U is Ug, which is minus 1 over f rho 0 dyp. Okay? But since we said that as a hypothesis we align the geostrophic flow with the x direction, we can say that this is equal to 0. So when we want to solve this equation, we can remove this, and we can substitute here f Ug. Okay? So at the end, what we will have to solve is this equation, these two second order equations in U and V. So now there are many different ways to solve it, this equation. One very nice that actually was made by one of your colleagues last year, maybe, or 2 years ago, was to consider a capital V equal U plus EV, and so multiply here by I, okay, and then finding the equation, which is something like alpha V. So of course,
for both equations, the first one does not have Vg.
no, because we said that we have aligned the geostrophic flow with x, so
Okay.
this is Vg is equal to 0, so the gradient in x of pressure is 0. But I mean, it's just how to say, simplification. You can also keep it, there is no problem. So if you rewrite this, you will have an equation like this, which of course gives you that solution are similar to A lambda z. So the capital V will have solution which are exponential. Okay? So in particular, the lambda which is the constant, the extinction constant, is equal to EF over the viscosity. So it's just a matter of how you prefer to solve this. You can follow what Ekman showed, or you can follow this, this solution here. So I don't want to go much more in detail. The only important thing is that I want just to write you the final equation, because now it's just mathematics. And what we have is that U is equal to UG1 minus E minus Z D. And V is equal to UG. Okay? So this is very important to have as a reference. So these two are the solution of the bottom Ekman layer. Both of them, of course, are depending on the geostrophic flow, the interior geostrophic flow. In particular, you can say that if Z is much larger, so D is this one, which is nothing more than this one. Okay? So the constant which rules how large is, how deep is the Ekman layer is exactly has the same form that we found at the beginning by simply considering Ekman equal to 1. Don't forget that F, if you put F equal to 2 omega, you find exactly this form here. Okay?
Okay, that is 2.
That is true.
2, I thought.
Yes, 2. Yes. Of course it's true. So this is the measure of the Ekman layer. And we can say that when Z is much larger than D, so it means that Z over D is much larger than 1, this term here goes to 0, so U is just UG. And this V is just 0. Okay? One more thing, and then I will leave you, is that if you take the value of Z going to 0, so it means Z over D, much smaller than 1.
Sorry, that's Z.
Much smaller than D. Okay? So is Z going to infinite. Very far from the boundary layer. So I am in a position Z which is much larger by D, which is the dimension of my boundary layer. Okay?
So Z by D would be
Z by D much larger than 1. On the contrary, Z over D much smaller than 1. So when Z by D is much smaller than 1, E, the exponential is order 1 minus Z over D, according to Taylor expansion. Cosine of ZD is order 1, and sine Z over D is order Z over D. Okay? So we can say U is equal to UG, 1 minus the exponential, which is 1 plus Z over D, and V is equal to UG, again 1 minus Z over D, multiplied by sine, which is Z over D. So it is UG Z over D, and then I have a term which is second term Z squared D squared, which of course will be much smaller than this one. Okay? So U and V in first approximation, when we are very close to the bottom, are exactly the same. So what we obtain as the solution of the bottom Ekman layer is a interior which is geostrophic. Now then we have a decreasing up to U equal to 0 in a Ekman layer which has dimension D. And if we go to represent the velocity when we are in the northern hemisphere, the velocity in this direction, in this way, which is called hodograph. So I put the component U on the x-axis and the component V on the y-axis, and every dot of this figure is a value of Z over D. Okay, so it's a dimensional. So if when I am here, Of course, z over d is equal to 0. This is a constant, so z is equal to 0, so u and v are equal to 0. When I'm here, u is equal to u geostrophic. In every part, every single point, I have different value of z over d. And in particular, very close to the bottom, I will have that u and v are exactly the same. So, close to the bottom, the velocity, since even if I have an interior flow which is directed along the x, I will have close to the bottom a velocity which is like this one. Well, like this one. Okay? So, on the left, with respect to the interior geostrophic flow. And this form here is called velocity spiral. The deflection is to the left of the current above the layer. Of course, the reverse holds for the southern hemisphere. Okay?